Assalamu alaikum. So yesterday we were discussing quantization and we left on this picture. This picture shows you peak-to-peak voltage from minus VP to plus VP, and that voltage is divided into 8 levels, into L levels. So L is the total number of levels that we have used to represent this peak-to-peak voltage. Now remember that L should be the power of 2. Like 2 power L, that L will be small. Uh, so like in previous example of quantization where we have taken as L is equal to 3, that is 2 power 3, that is 8 levels. And those are divided into different voltage levels. Like here it is from minus Q over 2 to Q over 2. If you say Q is 1, then it is 1 over 2 to 1 over 2, and then Q over 2 to 3, Q over 2, that is 3 by 2, then 5 by 2, and so on. So the mean squared value, that is noise variance, of the quantization error is given by from minus Q by 2 to Q by 2. So that is the maximum step size that we have from one level to another. So this limit is the step size. E square is the error. And what is the probability of the occurrence of that error is P of E, and GE is equal to. So the maximum probability is 1 over Q. So it depends on Q. If Q is 1, the maximum probability will be equal to 1. Q if any other value, then it will be any other value. So we solve this integration and we will have 1 over Q E square. Integration of E square will be E power 3 over 3. Then if you put the limits, it will be equal to Q square over 12. So that is your variance, the noise variance of the quantization error is Q square over 12. Whereas the peak power of the analog signal can be expressed as P is equal to Vp square over R. If R is equal to 1 or normalized 1 ohms, then P will be equal to Vp square by 1, and Vp square is equal to Vpp by 2 whole square. So this is incorrect. This 2 should be here. This Vpp by 2 whole square, and that equal to L square Q square over 4. Because if we go back and see the Vp is equal to minus Vp over to Vp, that is you are equal to 2 Vp. So 1 Vp, that is one side positive, will be equal to Vpp by 2 and its whole square. So that will be equal to Vpp square by 4. And Vpp is nothing, but it is equal to L into Q. L is the total number of levels and Q is the step size. So when we multiply Q with L, you will get Vpp. So we replace Vpp with LQ. So it becomes L square Q square by 4. That is your power. Then you can say the signal. So this is your signal power, and this is your noise power. That is, we have here noise variance. Then the signal to noise ratio can be calculated as L square Q square by 4. and q square by 12, and that will be equal to 3L square. That is how we calculate the signal to noise ratio to the quantization noise. Then we have non-uniform quantizers have unequally spaced levels. The spacing can be chosen to optimize the signal to noise ratio for a particular type of signal. And it is characterized by variable step size. Quantizer size depends on signal size. So another type of quantization other than uniform is non-uniform quantization, where the step size is not equally spaced. It is variable. Some information transmitted with small steps, small quantization steps, and some information transmitted with large quantization steps. So many signals such as speech has a non-uniform distribution. So let's first see figure 2.17. So this is speech signal magnitude relative to the RMS of such magnitudes. So the distribution is not uniform, as you can see. Uh, when magnitude is 0 and it's 0.7, and so the magnitude drops, so as the probability. So basic principle is to use more levels at regions with large probability density function. Concentrate quantization levels in areas of largest PDF, or use fine quantization, small step size for weak signals, and towards quantization, large step size for strong signals. Large PDF means large probability density function, where we can say that there are some information which might be having some probability of error, and that information may be sensitive or the signal is weak there. So those parts of the signal will be transmitted using small step size or the large number of levels compared to the strong signal. Those can be transmitted with large step size. So how we perform this non-uniform quantization? It is performed through compending. Now, compending is a method of compression and decompression. As you can see, at the input we have a compressor and the output we have the expander. So combined, we call that compending process. Compending the compressors COMP and expanders ANDING. So that makes it compending. So it's a compound word uh, made from compressor and expander. So it is a method of reducing the number of bits required in ADC, in analog to digital communication, while achieving an equivalent dynamic range or SQNR. Signal to quantization noise ratio should be high. We want to achieve high SQNR. That means the noise is low and power is strong. Signal power is strong. So that is a method of reducing the number of bits. So in order to improve the resolution of weak signal within a converter and hence enhance the SQNR, the weak signals need to be enlarged or the quantization step size decreased, but only for the weak signals. So as we are discussing quantization, and at the start I told you that as we increase the number of levels, the probability of occurrence of error will reduce. We also take an example where we have 8 levels and we have a actual sample taken at 1.3 and but 1.3 was not available, and the next step size, the nearest step size was 1.5. So we have to take 2.2 volt as an error. Similarly, if you increase the number of levels from 8 to 16 there, then the step size was reduced from zero point 0.5 to 0.25. Now you have like nearest step size available of 1.25 or 1.3. In that case, the difference between the actual sample value and the available quantization level available is 0.05 volt. So that means you have reduced the difference between the actual level and the available quantization level. So if we have more levels for a signal, whether it is weak or strong, you can be able to reconstruct that signal without any noise. So if it is already a weak signal, then you must transmit that weak signal through small step sizes so that the quantization noise can be reduced, so that the SQNR of that particular part of the signal should be increased, can be increased. However, strong signals can potentially be reduced without significantly degrading the SQNR or alternatively increasing the quantization step size. So compounding is a process where it tells us that we must increase the uh, step size for strong signals and we must reduce the step size, or we use more number of levels for weak signals compared to the strong signals. So the compression process at the transmitter must be matched with an equivalent expansion process at the receiver. So it's a two-way process. The forward application of this process is done at the transmitter, and reverse application to recover the original input, and the output is performed in the reverse direction at the receiver side. As you can see in the figure, before ADC conversion, we have this compressor that will compress the signal, and accordingly we will use different number of levels in the ADC step. Then we have transmitter, then channel receiver. We convert that signal back to analog, and then we have the expander that will undo the compressor that we have done at the transmitter. The signal below shows the effect of compression, where the amplitude of one of these signals is compressed. After compression, input to the quantizer will have a more uh, it is I'm just explaining the effect of compressor. We haven't discussed it yet. It is here. You can see in this figure, we have a actual signal is like this one, which has a large amplitude. The job of compressor is to reduce the amplitude of this actual signal from this large value to this small value. So that is the job of compressor, that it compresses or reduces the amplitude of the signals which we want to compress. When we do compression, as we do in the files, we compress files means we reduce the size of the actual file so that we can email it or some other purpose, we compress it. Similarly here, if a signal is transmitted with a large voltage level, compressor will compress that signal to a small voltage level so that we can reduce the step size. So after compression, input to the quantizer will have a more uniform distribution after sampling. At the receiver, the signal is expanded by an inverse operation. The process of compressing and expanding the signal is called compending. So the technique used to reduce the number of bits required in ADC or DAC while achieving comparable SQNR. Basically, to reduce the VP, that is a peak voltage. Like previously, we saw that we have voltage, like here we will have voltage from minus VP to plus VP, that is peak to peak voltage, that is VPP, and VPP is equal to twice of VP, or VP is equal to VPP by 2. So if you have large voltage values or the higher VP, then the number of levels will be higher, because we say that VPP is equal to LQ, and L will be equal to VPP by Q, where Q is the step size. So L is directly proportional to VPP, that is the peak to peak voltage. So number of levels will be more if we have the higher peak to peak voltage. So the compressor function is here is to reduce this VPP. So if you reduce to able VPP, that means you are reducing the number of levels required to transmit the signal. So if you reduce the number of levels, that you means you are reducing the number of bits, because number of levels is directly proportional to number of bits required to transmit a particular sample. If there are 8 levels, then you only need 3 bits. If there are 16 levels, you need 4 bits. So higher the number of levels, higher bits will be required to transmit a particular sample, quantization sample, or to encode, we need more bits to encode that particular information. So compressor compresses the amplitude of the input signal. Is it clear? So by doing it, by reducing the amplitude of the input signal or reducing the VPP, it introduces a non-linearity into the signal. So this maps a non-uniform distribution into something that more closely resembles a uniform distribution. So that means if an original signal is transmitted or has the large VPP, we compress it, then that means that we now have a non-uniform distribution into something that more closely resembles to uniform distribution. Actually, it's non-uniform distribution, but it resembles with the uniform distribution. Means in this particular signal, there may be some parts in this signal, in the original signal, that may be weak in amplitude. Like if you start from here, so low amplitude, low amplitude, low amplitude, but these peaks are have the high amplitudes. So low amplitude means weaker signals. Now, when you compress the signal, now weak signals and the peak signal will be transmitted with the compressed quantization levels. Means if we using like 8 levels for a 12 voltage peak to peak voltage, then from 12 to we reduce this to like 6 voltage. So we reduce it by half. Now, if we use the same number of levels to transmit the data, that means you are using twice the double of the step size, more number of levels, 2x more levels used to transmit the same data as we did without the compression. So that means we are mapping a non-uniform distribution into something that more closely resembles a uniform distribution. A standard ADC with uniform spacing between levels can be used after the compender. The compending operation is inverted at the receiver. There are in fact two standard algorithm-based compending techniques. So compending the compressor and expanding can be done through certain law. There are two laws. One is followed in US and one is followed in European. So the one that is micro mu law and one other is A law compending. So this is logarithm expression. Y is equal log of x is the most commonly used compender. This reduces the dynamic range of y. You can see that when mu is equal to 0, uh, it's a solid line, and as we increase the mu, it will now resembles the original input signal, which is like this one. So the higher value of mu will ensure the originality of the signal, and it reduces the dynamic range of y for different values of mu. This is the formula to calculate the y from the given input signal. X and Y represent the input and output voltages. Mu is the constant number determined by experiment. In the US, telephone lines uses compending with mu is equal to 255 that samples 4 kilohertz speech waveform at 8,000 samples per second. Encodes each sample with 8 bits, that is 256 quantized levels. Hence, data rate achieved is equal to 64 kilobits per second. When it is 0, that corresponds to uniform quantization. And ALA, for ALA, Y and X represent the input and output voltages. A is equal to 87.6, and it's the constant number determined by experiment. So same as here, we have different expressions for the two compending law, where we have mu 256. Here we have A, and its particular the specific value is 87.6 that is used after the experiments. Then we have pulse modulation. Recall that analog signals can be represented by a sequence of discrete samples, output of sampler. So the pulse modulation results when some characteristics of the pulse, that is amplitude, width, or position, is varied in correspondence with the data signal. So pulse modulation means change the pulse amplitude, width, or position. That means we modulate the pulse with respect to the input data. Either that change can be in amplitude, we change the amplitude of the pulse with respect to information, or we change the width of the pulse with respect to information, or we change the position of the pulse with respect to information. So amplitude modulation, you already know, like A modulation, where we change the amplitude of the carrier with respect to information signal. But other cases, we have width or position, where we change the width or position of the pulse with respect to the information signal, where amplitude will remain the constant. In the first case, when we have the pulse amplitude modulation, the amplitude of the pulse will vary with respect to the information. So here we have two types of pulse modulation. One is pulse amplitude modulation and one is pulse time modulation. Pulse amplitude modulation is simple, or you can say we have used this amplitude modulation in other forms as well. The amplitude of the periodic pulse train is varied in proportion to the sample values of the analog signal. So this pulse modulation is the third step that we do have. Uh, so here the input signal is your sample values of the analog signal. So discrete time, discrete valued signal may be the discrete time continuous value signal may be the input to this pulse amplitude modulation. So we have the sample values of the analog signal that will be the input. According to those values of the sample, we will change the amplitude of the periodic pulse train. Hence, it is called pulse amplitude modulation. Then we have pulse time modulation that encodes the sample values into the time axis of the digital axis. And it has two types. One is pulse width modulation, constant amplitude, but width varied in proportion to the signal. Means width of the pulse will be varied according to the information or proportion to the signal. Whereas pulse duration modulation, sample values of the analog waveform are used in determining the width of the pulse signal. So width modulation and duration modulation has little difference between them. In the first pulse width modulation, it says that it should have the constant amplitude, whereas the width varied. In pulse duration modulation, there is no condition of the constant amplitude. It says that sample values of the analog waveform are used, mean the sample values that the input signal is used in determining the width of the pulse signal. And it is not concerned with the constant amplitude. So here you have like uh, pulse code modulation signaling. First is 8-level signaling. B is 2-level signaling. In 8-level signaling, as you can see, we have represent every pulse with a certain number. That number depend on the number of levels that we use. So here it is the highest number is 7. That means we have used 8 levels. That is 2 power 3 is equal to 8, and that is 0 to 7. So the sample value of labeled as 5 then can be represented as 101. So that is the pulse train. So we convert this single 8-level signaling into 2-level signaling using the pulse train based on the labels that we have used to them. Then we have the PCM waveform types. The output of the A to G converter is a set of binary bits. But binary bits are just abstract entities that have no physical definition. So we use pulses to convey a bit of information. Example, a high voltage represent one binary, a low voltage represent 0. So in order to transmit the bits over a physical channel, they must be transformed into a physical waveform. So it is not like that we transmit 1 and 0s over the physical line. We transmit their waveform. That waveform represent these information 1 and 0s. Basically, that is the information that we want to transmit, digital transmission. But that information of one and zeros transmitted over the physical line into the waveform, into some kind of voltage levels. So a line coder or baseband binary transmitter transforms a stream of bits into a physical waveform suitable for transmission over a channel. So line coders use the terminology mark for one and space, that means zero. In baseband systems, binary data can be transmitted using many kinds of pulses. And there are many types of waveforms. Uh, Depending on their perform criteria, each line code type have merits and demerits. The choice of waveform depends on operating characteristics of a system, such as modulation, demodulation requirements, bandwidth requirement, synchronization, and receiver complexity, and etc. So these are the goals of line coding. Qualities to look for means a better line coding should be self synchronized, and it should have low probability of bit error. Self synchronization, it is the ability to recover timing from the signal itself. Means it should not be using explicit signals for the synchronization or the timing. It should be inherently having this timing information, so we can recover the timing information from the signal itself. It is also called safe clocking, safe synchronization, ease of lock or signal recovery for simple synchronization. Long series of ones and zeros could cause a problem. Whereas low probability of bit error, that is, receiver needs to be able to distinguish the waveform associated with a mark from the waveform associated with a space. So means when a signal is received at the receiver should be able to distinguish between the two waveforms. Because when we transmit one and zeros, it is the waveforms from where we have to recognize that whether the received information is one or zero. So there should be a clear and distinct difference between the waveforms of the mark and space. Bit error rate performance, relative immunity to noise. So that is too much to ask. There will be some noise, but the noise level affecting the line coding should be as minimum as possible. Immunity to noise means it will not be affected by noise, which is ideal condition. But in reality, there will be some noise that should be affecting your signal, but that level of noise should be as minimum as possible, so that should not be uh, introducing any error. It should not be increasing any bit error rate. Error detection capability enhances low probability of error. So if a line coding has some ability to detect uh, our capability to detect any error, that will enhance the probability of error. So if you know that one some information has been recovered in error, you can correct that information as well. So that will improve the probability of error. A spectrum suitable for channel, spectrum matching of the channel, that is presence or absence of DC level. So when we line encode, we have binary levels, we have bipolar signals, uh, we have different voltages, positive and negative. So DC level will be created when we have uh, mismatching number of positive and negative voltages. That will introduce the DC level. If the number of positive and negative voltages are same, or the number of positive pulses and negative pulses are equal, then there will be no DC component, there will be absence of DC level. In some cases, DC components should be avoided. The transmitted bandwidth should be minimized. If there is DC component, then you need the more bandwidth. Power spectral density, particularly its value at 0 PSD, of course, should be negligible at the frequency near 0. Means it need minimum power to transmit the signal. So it's at frequency, no frequency transmitted, doesn't, its PSD should also be negligible. Transmission bandwidth should be as small as possible. Transparency, the property that any arbitrary symbol or bit pattern can be transmitted received, that is, all possible data sequence should be faithfully reproducible. Then what is line encoder? The input of the line encoder is the output of the A to D converter, or a sequence of values AN that is a function of the data bit. So AN is your data bit that will be input to a line encoder, and the output will be an ST, that is a waveform. Where FT is a pulse shape and TB is the bit period. This means that each line code is described by a symbol mapping function AN and the pulse shape F of T. Details of this operation are set by the type of the line code that is being used. So this is the summary of major line codes. We have categories, as I told you, bipolar, polar, unipolar, bipolar, also known as AMI, pseudo-ternary, represents one by alternating signal sine pulses. Then generalized pulse shapes, NRZ, RZ, Manchester. You must have learned these in your junior semesters. So we just skip these and we move to next slide. So these are the some rules mentioning the some NRZ and RZ codes. So AN is equal to plus A minus A when XN, that is input, is equal to 1 and XN is equal to 0. So this is polar NRZ that uses NRZ, non-return to 0 pulse shape. It's very simple. For 1, it is 1. That is A plus A voltage for 1 and minus A voltage for 0. 1, 1, 0, 1. Whereas the second is polar RZ, that is RZ is return to 0 and uses the return to 0 pulse shape. Means you represent input 1 with plus A. We represent plus A, but we have to return to 0. We move forward, we have 0. We represent it by minus A voltage, but we have to return to 0. Again, see here, we have positive voltage, but we didn't return to 0. See, we didn't return to 0. We continue with this positive voltage. Unless we reach at another bit that is 0, then we have to move to the minus A. Then again, the next bit is 1. So we have to move from minus A to plus A. But there is no such movement from plus A to minus A. This is half pulse representing a bit with plus A, half bit, half pulse, half width pulse is representing 0 with minus A. That's why it's called return to 0, and this one is called non-return to 0. This one is polar NRZ and this one is polar RZ. Polar means they have the different polarities, plus A and minus A. Similarly, unipolar, that is one polarity and it is non-return to 0. But in that we have only one voltage plus A. There is no minus A, and it's a minus A, we have 0. So binary 1 is represented by plus A. 0 is represented by 0. Simplest. And 1, no need to return to 0. Continue with the high voltage unless the next bit is 0. That will be represented by 0. Then we have high voltage and so on. So that is your unipolar NRZ line code. Then with bipolar line codes, we have a space is mapped to 0 and a mark is alternatively mapped to minus a and plus a. As you can see here, an is equal to plus a and minus a, alternatively representing 1, and 0 is represented by 0. So this is alternate mark inversion. It's also called pseudo ternary signaling because we have three levels. Uh, it can be RZ or it can be NRZ pulse shape. You can use any. This one is RZ, bipolar RZ, that is bipolar RZ AMI. So the first one is plus, second one is negative, alternate, alternate. So if it starts from positive, next one it will be negative, positive, negative. So in this particular code, we have only four. So you can cancel out this one with this one and this one with this one. So the DC level or the DC value will be equal to 0 because we have equal number of positive and negative waveforms. Is it clear? Then we have Manchester line code. Use the antipodal mapping and the following split phase pulse shape. So within the Manchester, we have like for one, we have a positive voltage. And when it reaches at the mid, it transits from positive to low. And when it moves, if it is the next bit is 0, it will not transit at the start. For 1, it will transit at the start. For 0, it will not transit at the make a transition at the start. So it will carry continue or carry on with the negative voltage unless it reaches at the mid of the second bit, that is 0. Then it will make a transition from negative to high, and then will it keep on moving, and it will not transit at the start of 1, and in the middle it will again make a transition. Then the next bit is 1, then we will make a transition, transition, no transition, no transition, then a transition, no transition, and then we make a transition. So if it is 1 after 0 or 0 after 1, we don't make any transition at the start. If there are two consecutive ones, then we make a transition at the start. So that is the rule of Manchester coding. This is the summary of line codes. So you might have covered few of these or maybe all of these in your junior semester. So this is how we compare the line codes. Different line codes are compared here. So we take a break of 5 minutes. We will continue from this slide. So comparison of line codes, self-synchronization. Manchester codes have built-in timing information because they always have a zero crossing in the center of the pulse. Polar RZ codes tend to be good because the signal level always go to zero for the second half of the pulse. NRZ signals are not good for self-synchronization. So if you choose a code that need to be self-synchronized, you must go with the Manchester because they have the built-in timing information. Whereas Polar RZ, they are also good because they always return to zero. NRZ are not good for self-synchronization. Error probability, polar codes perform better, are more energy efficient than unipolar or bipolar codes. So if you go with the error probability, then polar codes are the best choice. Channel characteristics, we need to find power spectral density of the line codes to compare the line codes in terms of the channel characteristics. Different pulse shapes are used to control the spectrum of the transmit signal. No DC value, bandwidth ETC, guarantee transitions, every symbol interval to assist in symbol timing recovery. So power spectral density of line code, see figure 2.23, page 90 of Bernard Escolar. After line coding, the pulses may be filtered or shaped to further improve these properties, such as spectral efficiency and immunity to ISI. Distinction between line coding and pulse shaping is not easy. DC component bandwidths. DC components, unipolar NRZ and polar NRZ and unipolar RZ all have DC components. Bipolar RZ, Manchester NRZ don't have the DC components. This is the figure 2.23 spectral density versus the uh, normalized bandwidth, where T is the signal pulse width. So these are the different power spectral densities you can see. That is watt per hertz. First null bandwidth, unipolar NRZ, polar NRZ, and bipolar all have first null bandwidth of RB is equal 1 over TB, where unipolar RZ has first null bandwidth of 2 of RB, twice of the bit rate. So unipolar NRZ and polar NRZ has bandwidth, and bipolar all have bandwidth equal to bitrate. Whatever the bitrate is, that will be their bandwidth. Whereas unipolar RZ need twice of the bitrate of the bandwidth. मतलब कि जो भी bitrate है उसके double उसको bandwidth चाहिए. So it has high requirement of bandwidth. Whereas Manchester also has more bandwidth requirement, same as unipolar, although the spectrum becomes very low at 1.6 RB. So this is how line codes are generated. We have a ROM where we like this define the rules. Then we have make impulse. Then we have H as equal P of n. Then we multiply n P of n. So the FIR filter realizes the different pulse shapes. Baseband modulation with arbitrary pulse shapes can be detected by correlation detector, mesh filter detector, that is most commonly used. So we haven't done this mesh filter detector. We will cover that in next lecture. Then we have this bits per PCM word and M array modulation. At the end, you have some numericals. So this is how many bits shall we assign to each analog signal. For telephone, each speech sample is PCM encoded using 8 bits, hence 250 relay 6 levels per sample. The choice of number of levels or bits per sample depends how much quantization distortion can be tolerated with the PCM format. So this we have established already that large number of levels, that means we will have low quantization. Magnitude of the quantization error is E, and it should be less than or equal to the fraction P, the peak to peak analog voltage VPP, as follows. So E should be less than or equal to portion of the VPP. Since the quantization error can be no longer greater than Q over 2, where Q is the quantiler interval, we can write E maximum is equal to Q over 2, where Q over 2 can be written as VPP by L minus 1 multiplied with 2. So that is approximately equal to VPP by 2L, where L is the number of quantization levels. For most application, the number of levels is large enough so that L minus 1 can be replaced by L, as was done above. Then from equation 2.24 and 2.25, we can write, and hence L is greater than or equal to log of 1 over 2p bits. So it is important that we do not confuse the idea of bits per PCM word denoted by L in equation with the M level transmission concept of K data bits per symbol. So this can only be understood when you do some numericals. They are given here. One numerical, I show you the solution. Let's first read out this example 2.3. The information in an analog waveform with maximum frequency 3 kHz is to be transmitted over an M array PAM system with the number of pulse levels is 16. So this is M is equal to 16, not L. So do not confuse with this M is equal to 16. The quantization distortion is specified not to exceed plus minus 1% of the peak to peak analog signal. Means this 16 is that is these are different levels, pulse levels, and that is 16. The quantization distortion is specified not to exceed plus minus 1% of the peak to peak analog signal. That is portion of the peak to peak. 1% means 0.01 of the VPP. What is it is asking what is the minimum number of bits per sample or bits per PCM word that should be used in digitizing the analog waveform. So it is asking you L, small l. In A, in B part, it is asking what is the minimum required sampling rate, f of s, sampling frequency, f of s, it is asking, and what is the resulting bit transmission rate. So it is asking you bit rate. What is the PAM pulse or symbol transmission rate? PAM or symbol का भी पूछ रहा है. And if the transmission bandwidth, including filtering, equals 12 kHz, determine the bandwidth efficiency of this system. So let's answer all of these. Using equation 2.28, we can calculate A part for L, that is small l, that should be greater than or equal to log of 1 over twice of P. P is 1%, that is 0.01. So 2 into 0.01, that is 0.02. If you solve, that will be equal to 5.6. So 5.6 is not a number, so we will go with the L. That is 6 bits per sample to meet the distortion requirements. That means 2 power 6. And 2 power 6 is equal to 64. So 64 levels or 6 bits per sample need to be used to avoid SQNR, high SQNR. Then in the B part is asking you the sampling rate. Sampling rate we calculate by taking the double of the maximum frequency component, which is in this case is 3 kHz. So sampling frequency will be equal to 6,000 samples per second. So from part A, each sample will give rise to a PCM word composed of 6 bits. So every sample will be represented by 6 bits. Therefore, the bit transmission rate will be equal to 6,000 into 6. That will be 36,000 bits per second or 36K bits per second. Since multi-level pulses are to be used with M is equal to power K, that is 16 levels, then K is equal to 4. Yes, K is equal to 4 bits per symbol. So that is 4 bits per symbol. Therefore, the bit stream will be partitioned into groups of 4 bits to form the new 16 level PAM signal. And the resulting symbol transmission rate will be equal to 36,000 divided by 4. That will be 9,000 symbols per second. and the bandwidth efficiency is equal to number of bits transmitted per hertz. So that is bits, that is 36,000 per hertz, that is bandwidth 12 kilohertz. So the efficiency comes as 3 bits per second per hertz. So this is how we can solve this example 2.3. Similar example is given 2.14, and rest of the examples are given next. So please solve 2.14 and send the solution by tomorrow. Okay, so 2.14 you should be solving and send its solution by tomorrow, and that concludes our this lecture. So our next lecture will be on demodulation and detection, where we will learn the mesh filter and other things as well. Uh, these are the contents of this chapter. Uh, Detection of binary signal, Gaussian noise, mesh filter, base decision criterion, maximum likelihood detector, and error performance. So we will do it in the next class. Uh, some people are asking about the mid semester. It is from 22nd May, but we haven't got any notification from the university or administration, so we are unaware of that. If anything comes to my knowledge, I will share with you. We will try to cover this lecture tomorrow, which is highly unlikely, but I will try so that we could have the sufficient stuff for the mid exam. Okay, so we will continue with this lecture tomorrow, inshallah. If you have any question up to this point, you can ask.